Okay. And view slideshow. There we go. Hopefully you can see it okay. If not, let me know. But so this is week 3, bringing up this chart that we've seen several times now. For the most part, this chart is pretty much gone. So at least in terms of power, we're not going to be doing power too much anymore, but we are still going to be heavily rooted in Ohm's law. So that's using volts, amps, and ohms, or resistance, voltage, and current. So that's going to come up this week. Okay, so last week we talked a lot about series circuits, which is shown here, which is where you have, a single pathway for your electrons to go. And, there's only, if there's a break somewhere along the series circuit, that means that the load isn't going to work. Whereas, and last week we talked a lot about how to calculate total resistance for series circuits. So it's just taking the sum of all of those resistors. So this week we're going to focus on this side of things now. So we're going to be talking about parallel circuits and how to calculate the total resistance for those. So it is a little bit more difficult, and it requires a little bit more math in order to calculate total resistance for parallel circuits. And that's just because it's a little more complicated because we have all of these different pathways for our electricity to flow. But just a couple ideas from last week that are important concepts to remember. So for one, Kirchhoff's law we talked about, and that was that the voltage, if you can remember from last week, the voltage of the battery always equals the voltage drops on all of the resistors. So last week we learned how to calculate voltage drops, which is a super crucial calculation that has to be done in later weeks. So definitely knowing how to calculate voltage drops is important. So for example, in a series circuit, we only had one loop, right? But however many resistors had to add up to 12, so voltage would, be split among them. So voltage is, and this is saying if we have like a 12 volts. So basically just voltage is constantly split among all of those resistors. So that's why we have those voltage drops. So that's why I have this sentence in here too. But in a parallel, we have many loops. So like looking at this diagram, you can see my mouse here. This is a full loop, this is a full loop, and this is a full loop. So there are multiple pathways or multiple loops for electricity to flow, which means that each of those loops has to carry full voltage of the battery, which makes sense, right? Because all of these loops have to, electricity is it's even throughout. So we need the same amount of voltage going through all of these different loops. So that's why in parallel, each loop again has the same amount of voltage, whereas in series, all of there was those voltage drops. So voltage drops isn't something that we're going to really be calculating for parallel circuits. So that idea from last week goes away this week, but it comes back up in weeks to come. And then just this last point here, so the voltage of each branch in a parallel circuit equals the total voltage. So I hopefully made that point clear, but again, that just means that each loop here, or the voltage of each branch, so this is considered a branch, whatever the voltage is here is whatever the total voltage is. So if you had a 10-volt battery, it would mean that each branch or each loop, this is 10 volts, this is 10 volts, and this is 10 volts. Likewise, if you have a 25-volt battery, it would mean that every single branch is 25, not like a series where we're going to have, voltage drops throughout. Okay, so last week we talked about this equation, just the sum of all resistances equals the total resistance. This week now we're dealing with parallel. So we have a little bit more of a complicated equation. It involves fractions, and which is why for the math this last couple of weeks, it relates to fractions, and I think it has you solve algebra problems that use similar equations. But so I know this looks a little bit overwhelming, this slide here, but really the only two things important, which I'm actually going to highlight, the only two important things that you really need to know from the slide right here are these two equations. Well, how can I highlight? So this equation here and this equation here. These are the two equations you need to know for how to calculate total resistance for a parallel circuit. So again, we learned how to calculate total resistance for a series circuit last week. Now we're learning it for parallel. And the equation you use depends on if you have two resistors or multiple resistors in your circuit. So if you remember from like the beginning of the week, I said, or last week, it doesn't matter how many resistors you can have in a circuit. It's going to depend at every circuit. So I guess just be mindful of that you can have 10 resistors like this example is showing. But basically, all of the math right here that's above this, you don't have to know this, but all this is saying is that this equation here equals this equation, but this one's more simplified. So you can do this more simplified equation when you only have two resistors. You have to do this more complicated equation when you have multiple resistors, and that's just because of the way the formula works out. So the way that this equation on the left works, so I'm going to do the simple equation first. Again, when you have two resistors, you can use this equation, and basically all this says is that you can calculate total resistance in a parallel circuit by multiplying the resistance values and then dividing it by the sum of both of those resistance values. So for example, let's say we had a resistance, an R1. Oh, that's not gonna work. Okay, I'm gonna type, that'll be better. So if we had an R1 that equal 5 ohms, and an R2 that equal, I don't know, 3 ohms, which again, this is resistance, right? We could calculate the R total or the REQ, that just says that means equivalent. It's the same thing as RT. We could do this by doing 5 times 3. So 5 times 3, which, oh, that's not a 5. 5 times 3, which is 15, and then divide that by the sum. So 15 divided by 5 plus 3 is 15 over 8. Or if you did the math there, 15 over 8 is 1.87. So RT equals 1.875. And again, I did that by just first multiplying the two resistances, which is 15, and then dividing it by the sum, which was 8. 5 plus 3 is 8. So that one's pretty simple. Just gonna highlight that one so you know. However, in situations when we have more than one resistor, we can't simply multiply and add the sum, because once you deal with 3 or more resistors, the math behind it gets a little more complicated. So you have to use this equation here. Well, sorry, I deleted my scribble around it, but we'll bring it back. So when you have more than 3 resistances, and this depends on 3 or more, I should say, if you have 3, 4, 5, 6, 7, and so forth, you're always going to use this equation. So there's really only 2 you have to remember. And if you can use this equation for just 2 resistances, so you can, like, if you wanted to, but I think this one's easier for 2. But for anything more than 2, you've got to use this one. And this one looks a little bit more complicated, but basically all it is first you have 1 divided by 1 over R1 plus 1 over R2 plus 1 over R3, etc. So basically what it's doing is it's taking 1 divided by 1 over all of the resistances. So how I always would recommend solving problems like this is because a lot of times when you if you just typed it into your calculator, 1 divided by whatever your R1, R2, R3 is, a lot of times the calculator will mess that up. So I would recommend first adding up finding the fractions for 1 over R1, 1 over R2, 1 over R3, finding whatever those fraction values are as decimals, adding that together and do 1 divided by that number. Which of this is confusing right now, which it probably is, because it is confusing to talk about it and not do an example. I'll do an example in a minute here, and hopefully that'll clear up how to use this equation. But okay, for now, this is an exact problem that you would get from your quiz this week. just different numbers. So in this example, we have a parallel circuit with two branches, both with on 100 ohms. What is the equivalent resistance? Again, equivalent resistance here is the same thing as saying total resistance. So I'm just gonna underline that in parentheses here, total resistance. And so we know here that we have a parallel circuit because it tells us, and we have two branches, both with the 100 ohms. 100 ohms, since it says ohms, we know that they're talking about resistance, right? Because ohms is resistance. So we can calculate the equivalent resistance, which is just the total resistance, by using that formula that I showed you a minute ago, which is, in simple terms, just this. So it is both of the resistance values multiplied divided by the sum. So since we know that both of them are 100, you can do 100 times 100 divided by 200. So if you type in on your phone or calculator 100, which is R1, times 100, which is R2, and divide it by 200, you will get 50 ohms, which is our total resistance. So you'll note that in this example here, the total resistance of 50 is less than what you started with. Sometimes it works out like that, and that's okay. But I'm going to pause. So this is important just to make sure you both, the one that you guys on the call here, does this make sense? How will you, basically all you need to know right now is, can you calculate equivalent resistance or total resistance when you're given two resistance values by using this equation? Is that clear on how to use this equation? If I don't hear anything, I'm going to assume this is clear. So again, just using this, okay, perfect, and thank you. Using this equation here for two resistances, definitely need to know that. But so in this example here, so this is when we have, this is an example where we're going to have to use that longer equation because we're given more than two resistors. So we have in R1, which is 50, in R2, which is 30, and in R3, which is 20. So what is the equivalent resistance? Well, so now since we have more than two, we can't use that simple equation where it's just multiplying them and dividing them by the sum. So we have to use this equation, which is a little more complicated. So how I would break this down is I would first find the fraction for each of I would find all of these components first. So I would write it out on your, if you write it out or if you just type it into your laptop or calculator, 1/50, which is R1, 1/50 is the part that's right here. 1/30 is the part that's right here, which is 1/R2, and then 1/R3 is 1/20. So if I were you, what I would do first is figure out what all of those fractions are. Decimals, just because dealing with fractions is, confusing, and it's also difficult to type into your calculator. So I would do 1/R1, which is 1/50, which is 2. 1 divided by 50 is 0.02. So we had 0.02. And the reason I would put 1 divided by here is because we have to divide all of this by 1. So we have 1 divided by 0.02 plus 1 divided by 30, or 1/30 is 0.03 plus 1/20, 0.05. Then, so basically, so once you calculate all of these fractions as decimals, like I did here, I would then add all of those together. So 0.02 plus 0.03 plus 0.05 is 0.1. And then we can just divide it. So 1 divided by 0.1, actually 10, but that's just because this was a rounding thing, obviously, but that's okay if so you might have to round in situations, so that's totally okay. But again, so the way you solve this equation is you just have to do 1 divided by the fraction of all of those resistors. And I'm just going to show this in math way since that might be easier for you. So to kind of show you how, there we go. So to show you how I would do this in math way, there's this fraction button here. But there we go. So there is this fraction button here, and you could just type it in like this. So 1/30 plus 1/, I think the last one is 20, wasn't it? Do 30, 50, 20. Okay. 30, 20, and then we can hit it, and it'll give us that number 9.6777, which you know, if I had 10, but it was just a rounding thing. So again, this is the equation you have to use, and you know, you would just continually add more. Like if we had another resistor, let's say that was R4 equals 40, R5 equals 2. You could just continually add them. So again, this is the equation that you're going to have to use for parallel circuits. Anytime you want to calculate total resistance and you have more than 2 resistors. So it's just 1 divided by the fraction of all of those numbers, with the resistor being at the bottom. So I just think that typing it in on a calculator or can sometimes be confusing if you don't have like a graphing calculator, or especially typing it on your phone is very easy to make mistakes. So for example, like if you just started typing in 1 divided by 50 plus 1, it wouldn't make it, your calculator wouldn't be able to read how it's written like this. So I would either when you're solving this week's quiz, I would either use Mathway and make sure that looks like this, where we have 1 over all of those fractions, or first find the decimals of all of this bottom half, add those together and do 1 divided by them. But this is definitely one of the more complicated equations that you have to use, and also it's one of the more complicated components, I guess, for this week that on the quiz a lot of people get wrong. So I'm going to pause here just to make sure. So I know this one was a little confusing, but does this concept of using this equation and how to use it make sense? Again, I'll just pause for a minute and make sure either of you have questions or concerns. Okay, I don't hear anything, but you know, let me know if you do. But again, this equation and this equation are the 2 new ones that come up this week. But okay, just a couple more slides. Might end a little early today. So the other idea that's kind of talked about in the last couple videos for this week is this idea of solving parallel circuits. So if you remembered last week at the end, we talked about how to solve series circuits and calculating the voltage drops at all of those locations. But if you remember what I said at the beginning, in parallel, since we have multiple loops, we always have the same voltage throughout. So there's really no point in calculating voltage drops. So we don't really do that for the parallel circuits. However, something different from this week is since we have all of these different pathways, we do not have the same current throughout all of these different branches. So in a series circuit, the electricity flows at the same current or at the same speed. At a parallel circuit, all of these different branches are going at different speeds. So that's essentially what we're solving for here. So if you look at this example, we have a parallel circuit with a 20-volt battery, which is shown here. It has 2 branches, right? 1, 2, 1 with a 20 ohm and 1 with a 40 ohm resistor. And then it wants us to calculate the current on both of those resistance branches, and then also the total current. So kind of works similar to how we calculated voltage drop, where we use the total, current and the resistance value at that location. So kind of what we're doing here. So in this example, I, which is current, again, that's what we're calculating, equals V, which is voltage, divided by R, where V is going to be your total voltage. and R is going to be your resistance at wherever you're trying to calculate the current. So for example, if we wanted to calculate the current at the 20 ohm resistor, or this branch, we would do V, which is 20, divided by R, which is 20 ohms. 20 divided by 20 is 1 amp, which means that the current right here is 1 amp, which I'm going to draw. So this here, we know that the current is 1 amp. Again, we know that because we can calculate the current at different locations throughout a parallel circuit. And that's a new concept we learned this week. So likewise, for the step 2, you can calculate the current at the 40 ohm branch, which is this one, by doing the same thing, which is just I equals V divided by R, where V is your total voltage of 20, and R is your resistance value at that given branch, which is 40. So 20 divided by 40 equals 0.5 amps, or 500 mAs. So again, the only thing different from step 1 and step 2 is that I was just calculating the current at different locations. And this isn't something we did last week because in series circuits, current is the same throughout. And so I'm just going to write 0.5 here because that's what we calculated. Okay, so hopefully that makes sense. So kind of just summarize all this up. Last week, what we did is we looked at series circuits and we calculated voltage drops because the voltage change throughout the circuit. This week, we are calculating the current at given branches because we know the voltage stays the same. So we're able to use that in our calculations to determine what the current is. So then the final step of this problem is that now, since we have the current at both locations, we can calculate the total current. So if you go back to this problem, they give us the voltage and the 2 ohms, but they don't give us the total resistance, and they don't give us the total current, but we can find it. So for this example here, you would do, I like this one better. So 20 divided by 40, where those are coming from, or where just to make sure we're all clear here. So this is just using that equation at the beginning, R1 times R2 divided by R1 plus R2 to calculate it. So 20, which is the 20 ohm times 40 ohms, which is this one here, the resistance, divided by 20 plus 40, which is 60, gives you 13.33, which is the total resistance. So again, this problem here, which I'm going to highlight or underline, this is just what we were doing before. So it's just, you can calculate the total resistance by multiplying. If you only have 2 resistances, like we do in this example, you multiply them and then divide it by the sum. So now that we have total resistance, we can easily calculate total current because we have all the values, right? We have total voltage, total resistance. So we can find total current by doing 20 divided by 13.3, which is the answer we just found, to get 1.5 as the total current. Okay, so again, what we did in this problem here is that we first calculated the current at a particular branch, then we calculated the current at the other branch, then we calculated the total resistance, which you really could have done this step before you didn't have to find the current to do this step, since all we did to find total resistance was use the resistance value. And then we calculated total current. So you're constantly, if you haven't notice the trend here, you're constantly using Ohm's law, which is that V equals I times R, or I equals V divided by R, depending on what you need. The only thing that's changing each week is sometimes you're not using the total voltage or the total resistance. You might have to use the resistance at a given point in time, and that just depends on what you're trying to solve for. So you really have to read the question and the problem carefully and make sure that you understand what is it asking for me to solve? Because if it only asks for the current on the 20 ohm branch, you only have to do this step. But if it's asking for the total, there are multiple steps you have to do to get there. So this can definitely be challenging, but once you kind of do it enough times and see it enough times, it definitely hopefully will start to make more sense too. But at the end of the day, we're always using Ohm's law, and that's a constant trend, and just breaking it down step by step and trying to figure out what they want you to solve for is the easiest way. So This slide I know looks confusing, but basically what I want to talk about now is the idea of Kirchhoff's law again. So it comes back up this week. And basically all of this confusing graph is showing is that you can calculate the current at a given point by just looking at where it is in the circuit. So kind of going back to this one because it's a little more simplified. You can see here that we calculated the total current solely by using math as 1.5, but it isn't a coincidence that the current here is 1 and the current here was 0.5. So something important about parallel circuits that we also learned this week is that at these junctions, which is the point at which the branch or the pathway switches, and there's multiple ways or directions that our electricity can flow, our current splits up. So we don't know the current that's here, right? But we do know the current that's in this area. So we know the current from this yellow circle to this yellow circle is 1 because that's the branch that 20 ohms on. We also know the current right here from this yellow circle to this yellow circle is 0.5 because that's the branch that 40 ohm resistor is on. So these here, which I'm going to circle these in a different color, to red, this is not considered a branch because our well, I'll make it black, I guess, but these black circles here aren't considered anything really because our electricity isn't splitting off at this current. It's just like turning, and it's essentially, this is just because the circuit's like a hypothetical easy way to write look at a circuit in real world, but in real world a circuit isn't always square. So these here, these corners, since the electricity is still flowing, there's not anywhere that's splitting up. So our current isn't changing. But at these yellow circles here, when our electricity flows from our battery and gets to this point, some electricity or electrons flow this way, and some can keep going and flow this way, right? And that makes sense because we know that we have multiple pathways, right? Some electrons take this pathway, and some electrons take this long pathway. So again, the reason I'm bringing all this up is because since we know the current right here in this branch and the current right here on this branch, at this point, those electrons are going to meet back up. So we have all of the current speed of 1 amp here and 0.5 amps here. And anytime you get to a point where they meet back up, it adds together, which means that the current right here after that junction is 1.5 amps. Which makes sense because that means that 1.5 amps is what's going into this voltage, which means that's the total voltage. And it also means that whatever you end with and whatever you start with is the same, which means that right here, the voltage or the amperage is also 1.5 amps. So to kind of show how all of this outlines together in this circuit, we have 1.5 amps going in here. And then all of a sudden it splits up at this first junction. 1 amp goes this way and 0.5 amp goes this way. And we know 0.5 amp goes this way because if we know we start with 1.5 and this is 1, we know that this side and this side have to add back up to what it was before, or because we know they're going to sum back together to add up to whatever that is. So 1 plus 0.5 is 1.5. And again, we didn't have to, you could solve that by looking at it, but you could also solve it by actually doing them. So basically the main idea here is that at these junctions, our current splits. When they come back together, they add up. And they don't always split evenly. Okay. So this example looks pretty intimidating, but we're going to just kind of walk through it. All this is showing is that same idea, and that same idea works even if you have something like this where you have 3 branches. So in this situation, we have a circuit, we have 3 resistors, 3 branches. We were given that has 12 volts, and we were also given the resistance at each of these values, 4, 3, and 2. So I was able to, or what this is showing is that we calculated or we can calculate the current at that location by just taking the total voltage divided by the resistance at that given time. So that's all that I'm doing in these 3 scenarios. 12 divided by 4, which is 12, the total voltage, divided by 4, which is the resistance at that branch, to give us 3 amps. 12 divided by 3 equals 4, which is 4 amps. 12 divided by 2 equals 6, which is 6 amps. So it's the same thing that we just did before, where, we are calculating our current at a given point in time, just like how we calculated the current at 20 ohm and the 40 ohm. We're calculating this one now at the 4 ohm, 3 ohm, and the 2 ohm. Okay, so once we have that, the other thing that we were given in this problem is that the total current was 13. So it told us in this problem that the total current was 13. And we weren't given what the current is at all on the rest of the outside. So we can easily calculate, right? So if let's bring these back, because I think these are helpful. We look at this one here and follow the path of electrons. The electrons are going to start at the battery, get to this, and we know they're going 13 amps here, because it tells us they're going to get all the way here, and then some of them are going to go this way, and some of them are going to go this way, which means that our our current's going to change. But if we know that this is 3 amps, because we calculated that this V1 here, then we know that this is just 13 minus 3, which equals 10 amps, because remember, at the end, they have to add back up together at this location. Okay, so now we know from here to here, we're going 10 amps. And then we know that it's flipped again, right? Because we calculated it here to 4 amps, which means that 10 minus 4 is 6 amps. So we have 4 amps going down here and 6 amps going all the way over here again, because these corners don't have any impact since there's not multiple loops at them. So 6 amps here, 4 amps here, and then they meet together again at this location. So we had 4 amps plus 6 amps to give us 10 amps at this location. So we have 10 amps going here, and then you can see that it meets back up with these 3 amps, 10 plus 3 to give us 13, which is what we started with. So I know that was kind of a long problem, but basically all this is showing you is that Kirchhoff's law is saying that at the point of a junction, which is anywhere where our current splits direction, the current before the junction is going to split up down the branches, and then at the end it's going to add back up. And if we know the current at either the beginning or at the one of the branches, if we know both of those, we can calculate what the branch is with the other one, because we know it's just a difference. Likewise, if we don't have the total current, if we have what the current is at one branch and what it is on the other, we can add them together to get what that total current is. So that's all Kirchhoff's law is showing you, is that even though the current is changing throughout the circuit, and the end, it's going to always start and end with the same value. So I know that was kind of a lot of information at once this week. It's a lot of information at once, but I'm gonna pause again and make sure that the idea of basically, so what I just showed you is the idea that how to calculate current on different branches, both like this way, where we're just simply subtracting and adding, and how to calculate it using math are going to give you the same answer, but knowing how to calculate both of them are important, because when we deal in later weeks with combination circuits, both of these ideas come up again. So does that make sense? What I just did, I don't hear anything. I'm gonna assume it does. But okay, so just the last thing I wanted to show, and this is a very simplified example, a lot more simple than this one. But basically, so a junction, that is, if you hear me say that word, that's just when our electrons or electricity splits direction. A node is what's considered just a corner. Doesn't really have any impact on your calculation. So just 2 terminologies to know. We have junctions here because this is where the electricity either splits directions or combines back together. These nodes are just corners. So in this example, this is a pretty simplified example, but one that you could get on the quiz this week. And it is as simple as we have a junction with 2 branches. Okay, so 2 branches, right? And it has 5 amps going into it with 1 amp going out of one of the branches. What is happening with the other branch? Okay, so we know that we have 5 amps going into this first junction, and we know that we have 1 amp coming out. Well, we can easily calculate what it is right here by just doing 5 minus 1, which gives us 4 amps, right? And the reason I know that is because they split up here and then they have to combine back at the second junction, which is here. 1 plus 4 to give us 5 right here. So again, all we showed here is that the current did change throughout this circuit, but eventually it ended and started with the same number. So that's really the main idea. I don't think you have a problem this week that this complicating having you do different circuits, but you do have a problem like this where you just have to simplify it like that. But it's only going to give you this. You're going to have to know how to make this diagram. Okay, so that's really all I had for this week. So just to recap what we learned. We learned how to use both of these equations. So we should know how to use both of those equations to calculate total resistance or equivalent resistance. It's the same thing. So they might use both of those terms in the quiz. So just be mindful that total and equivalent are the same word. So we did some examples of that. Then we were able to calculate the current at specific branches in a circuit by taking the total voltage divided by the resistance of that branch. And then we also took it a step further and just showed that, you know, what you actually end up finding in your calculation should make sense when you add and subtract them back together. So it's important to just draw your circuit because then you can easily calculate this. But yeah, so those are the main ideas, but now 20 minutes, which is good. So if there's questions, then I can do another example or explain it something clearer if that's needed. But if not, that is all I had. Hopefully that makes sense. I know this week can be kind of challenging, but I guess just a heads up too that gosh, I think if week 5 gets real, I always think week 5 is the hardest because it's using all of these terms in all of last week's terms and just combining them. So definitely make sure you understand this concept and how to use both of these equations and when to use both of them are the main ideas. But thanks.
All right, thank you very much.
Yeah, thank you. I'm gonna stop recording.